Hello everyone, in this second lesson of the unit we're gonna explain in some detail how to extract data for a heat integration problem. It is some concrete rules and guide to follow. First, don't maintain unnecessary too detailed features. For example, we're gonna try to extend a stream as much as possible, going from the starting temperature to the end temperature, summing up the heat needs of the stream along this change. Of course, it can be done if the thermal inertia, the slope of the stream in the T versus delta H diagram, is constant along the change, because we are considering stream as straight lines. If this is not the case, long nonlinear stream can be linearized by segments for calculation purposes. Imagine, for example, something that is heated first and then vaporized and then furthermore heated. But we must remember that the conceptual stream is one. Linearization is just the calculation trick to treat the stream as straight segments. At the same time, correct, if possible, strange behaviors like this up, and finally down temperature that happens more frequently than expected. Why taking out the temperature from 35 to 180 to finally take it down to 130? This is not logical. Remember, it is about disconnecting the current solution and find a better one. Second, when extracting nonlinear stream, do it the safe side. This is the side that gives you a security extra. It is, in cold stream, the safe side is up the real stream, and in hot stream, the safe side is down the real stream. Then take hot stream, the real one, hotter than the approximation, and real cold stream, colder than them. Third, don't include into the problem parts that are mandatory, compulsory, but that cannot be changed. For example, using quenching steam generation in a reactor that forms part of the reactor cannot be used in other places. And also true utility steams. It is utilities that cannot be replaced by any other. Quenching, as in reactor steam generation, cold shots for reactor hot spots control, steam in a shift reactor, steam injection for steam distillation, that is different from direct steam to reboil the column, that is only for heat transfer. Steam for steam distillation form part of the nature of the process. All this cannot be included in your heat integration study. Fourth, don't include into the problem, link energy flows. The energy flow of a reaction, for example, or the change in temperature linked to a compression or expansion. This cannot be integrated, cannot be used at heat in other place. This energy flow, 430 kilowatts, are shaft work, not heat that can be used in a heat exchanger. Look always for hidden heat exchange inside your process for direct heat exchange, mixing streams, injecting streams, process water, because heating and cooling opportunities are lost. See why. Here you are mixing a 600 Kelvin and a 300 Kelvin stream in order to get a 400 Kelvin one. Okay, you can do it and let the heat exchange directly. But it is better to see before if you can use this heating or this cooling in other part of the problem. If you do that, the heat exchange is then condemned to the current configuration that is not compulsory. You can take heat out or put heat in streams. It is better for your balance. In particular, heat exchange by direct mixing can involve heat transfer across the pinch. That is a way to expend more utility than needed, as we will see. One good way to calculate if you have to recover heat before mixing or not is calculating minimum heating and cooling, the targets, with and without the mixing streams. If results are the same, you can mix directly without previous recovery. If target change, perhaps it's better to study the recovery before direct mixing. And this is all for this lesson.